So, okay, we will continue from where we left yesterday. In the previous lecture what we did was I was talking about basically how to build up a larger dimensional switch or larger size switch using a smaller size basic switch elements, and in that sense what we want is the preservation of the certain property which we call a strictly non-blocking property. And of course, the question was whether I can reduce my cross point complexity in some way or not. First thing was the use of creating larger size by using a smaller thing and further reducing the cross point complexity. So, what we did was I took a case where we were trying to build up using 2 stages, and I took some switch with certain basically kind of a small n as the input ports, and then we build up the interconnect by using, if I am going to use n by n, I said that one link can go to each one of the switch in the output stage or in the second stage, but this was leading to a blocking situation. So, if certain inputs are free and as well as output is free, I cannot set a path between them in certain situations. So, in order to resolve that, what we did is we actually start using n by n square kind of switches were used instead of n by n, and in that case there were actually n wires which are going out, and this actually means I need to put n wires to each one of these. So, all these n can be connected to any one of these n without any blocking to happen. So far this number is going to be smaller than n, then it will not be possible, because whatever is left over and there is one which is free here cannot be connected, only part of the connections can be made. And of course, we figured out that the complexity still remains, because if you have only there are k such elements. So, you have switch size of nk by nk, which usually will require, if I build up a single crossbar, will require n square k square. In this case I will have a switch of n by n square, which becomes n cube complexity, and I have actually 2k such switches. So, I will be requiring O2 k n cube kind of thing. And then of course, if I actually take from here, you can actually clearly see that if I am actually making kind of k will become equal to n, in that case both will be O n raised to power 4, or since your capital N is nothing but technically equal to n square. So, this is nothing but complexity of O n square only. So, that is what we did last time, and then I thought, okay, we can go to 3 stage interconnection, and I defined a closed network in that case, and I also defined what is going to be strictly non-blocking structure, what is rearrangeably non-blocking, what is wide sense non-blocking, and what is going to be blocking structure. And then of course, I defined the closed network, which was you will have some inputs. So, for example, n input ports, and they are k such switching elements. So, total number of incoming ports is n into k, and we were connecting in the middle stage many such switches, and we have to find out what will be the dimension. Now, each switch should connect to each one of those switches. So, I will be actually having something like this. So, I might end up in choosing some number here, some middle stage. So, in fact, the way I defined it was this was not n, this was m1, this side was n1, this is also n1. So, all switches which were here was m1 by n1 switches, and I was using k1 of them. Then I was using the middle stage k2 switches, which was of m2 by n2 size, and then there was a third stage configuration, third stage switches, where I will be using m3 by n3, and there were k3 such switches. Condition is that only free incoming ports are available only in the first stage, and only free outgoing ports are available only in the last stage, which is the third one in this case, or output stage. none of the incoming ports and outgoing ports in the intermediate stage should be left free, they have to be connected. So, in that case the number of, because I need to connect everybody here, so this number, which actually means that M2 has to be equal to K1, because K1 actually lines will be coming and connecting onto this, and similarly here the number of inputs everywhere will be M2 will be equal to K1, and similarly now N1 has to be equal to whatever be the number of switches, in this case this will be equal to K2, and this also implies, because same structure will be applied here. So, you will have N2 will be equal to K3 and M3 will be equal to K2. So, you can see this condition. So, M3 will be always equal to N1 is equal to K2, this condition will always be satisfied. And I said this actually switch can become strictly non-blocking, and I took a very simple example. This will be later on proved as a Claus network. This is actually the Claus network. We will use a Claus theorem to find out what will be the condition for strictly non-blocking nature of this particular switch. So, if M1 minus 1 lines are already busy occupied here, the same is true at this place, that M1 minus 1 lines are occupied here. There is only one line which is left in which I am interested, there is only one line which is left in which I am interested. I want to connect these two. In worst case scenario, now these, out of these lines which I am putting here, M1 minus 1 are already occupied. They might be using certain middle stage switches for connecting to some incoming ports. From this side, in worst case scenario, these can be using a different set of switches, there is no overlap between them. If I had one more extra, this can always be used to set up the path between this free input and output link, and switch will be always a strictly non-blocking switch. You do not need to disturb any existing connections, okay, which actually implies that I need to have, if I am going to take a symmetric case whereby M1 is equal to N3, so you will find that I need K2 should be equal to or greater than or equal to 2 into M1 minus 1 plus 1. So, that is a condition which will come from this thing, and this is nothing but 2 into M1 minus 1. This should be the condition, and K2 will then actually decide what will be value of N1 and M3. Okay. So, a strictly non-blocking switch will look something like this. It will have M1 which is going to come in, and you will have these ports which is 2 M1 minus 1, and this will be going to various switches here. M1 ports, there are total K1 such switches. So, again this dimension will be 2 M1 minus 1, total number of switches will be 2 M1 minus 1, the number of ports here will be K1, and since I am actually taking M1 is equal to N3, so I will call it again M1, this will be also M1, and since you will have, in this case again these lines have to be 2 into M1 minus 1. So, number of middle stage switches will be these many, and these of course, because I want a symmetric thing, so I will be also taking this thing as a K1, K3 will be equal to K1, that is a symmetric case, and this will be the condition which will be satisfied. Okay. So, M2 will be equal to N2 in this scenario, this switch will also, everything actually is symmetric in this case, and this is a strictly non-blocking switch. Now, what will be cross point complexity for this particular switch? So, if I want to find out cross point complexity, number of cross points, I can very well estimate that for this particular switch I will be requiring M1 multiplied by 2m1 minus 1 number of cross points, and number of switches which are here is k1, and exactly similar stage also exists in the third one. So, I have to multiply it by 2, and then what I will have is how many middle stage switches will be required is 2 into m1 minus 1. What is the size of the number of inputs which are coming into this? This will be nothing but k1 number of inputs which will be coming in, and k1 will be going out. Okay. So, this is what will be the number of cross points. So, we can try to optimize this. We have to first of all find out what is going to be the value of, because the total number size is actually now n. m1 into k1 is what is your is a constant, and I need to find out what are the optimal values for these. So, I will write everything down in form of m1, and we will try to optimize with m1, and then find out what should be value of m1 for optimality, basically the minimum size of the number of cross points delta c. So, for this let me now first of all repeat whatever I have written. So, this is the total number of cross points. So, I will now replace all k1s by n by m1, so that I have only one variable sitting in there, so and I can take a derivative. So, k1 will be n by m1. So, this what we will get. We can also actually assume that let m1 be much larger than 1, so that I can now make an approximation to m1 minus 1 can be approximated as 2m1. This actually will simplify my life. So, approximately the cross points will be now varying as 2m1 into 2m1 into n by m1 plus and now solving this gets reduced. I will have 4m1 n plus 2n square by m1. Now, taking derivative delta c over delta m1 for the optimal value of m1, and then we will put that m1 value and find out the total number of cross points approximately and what is going to be their complexity. I can now actually keep this particular assumption true and then use this expression for finding out the number of cross points. So, once I take the derivative, this will turn out to be 4n plus 2n square minus 1 over m1 square, and I can make it equal to 0, and this will give me, in fact I can now reduce, this will be 2n, I can take out. So, this will be 1, okay, I will let me keep it as it is. Okay, so this actually implies either n is equal to 0, so which is the condition I am not looking for. So, I think this argument, if this is 0, this is what will give me the answer. So, this has to be 2 plus, so 2 will be equal to minus n by m1 square. So, m1 will be nothing but n by 2 root. So, this will be the answer. So, I can now put this thing in the to find out the number of cross points in this expression, and this will turn out to be 4 root of n by 2 into n plus 2n square by root of n by 2. So, this will turn out to be 2 root 2 n 3 by 2 plus again from here 2 root 2 n raised power 3 by 2 . So, now the complexity is now of the order of 3 by 2. So, we have now able to go from n square to this is lower complexity than what we had in a single crossbar. So, I am able to reduce my number of cross points. Of course, only thing is that now I have introduced complexity in terms of the routing algorithm, which is required because you have to search for a path and then you have to set up a path, but path can always be set up. So, this is a pretty efficient system. Now, before actually moving forward, I need to understand now this kind of switch requires large resources. Now, usually in network operations or whenever we do a practical design of a switch, we will never build up actually a strictly non-blocking switch because you do not require it. If I can introduce a very small amount of blocking probability, say 5% or 10%, and have much less hardware, probably I will be able to provide an acceptable service to the users. Okay. So, it is always a good idea that or I make a very small size strictly non-blocking switch and then I actually use what we call expanders and compressors, which basically is a special kind of a switch where large number of incoming ports are there on one side and smaller on this side, with the assumption that all users will not be active at any point of time. So, chances you will be blocked is very small, but because of which my amount of hardware reduction is much drastic, which will help in reducing the call cost. So, I will appreciate that. So, usually you will put a compressor like this, then is a strictly non-blocking switch of n by n. So, you are using some capital M which is going to be larger than n. So, either you will be using this kind of configuration for a switch, so where this will be strictly non-blocking switch, or you will itself will design a m by m blocking switch with less number of cross points, because every cross point require a management. So, in fact, cross point need not be actually physically made in this fashion. I can build up a strictly non-blocking switch even using time slot interchanger, which I will be covering sometime later in the lecture. And we need to estimate what is going to be the blocking probability if I build up a 3-stage structure, because I need to have a blocking probability estimation if I am going to design a blocking switch. Now, that requires some understanding of queuing theory. So, I am just actually digressing from here and moving to the what we call the probability or what we call state probability estimation in case of a switch. But before that, let me do a very simple queue, because this need to be understood, and I will use a similar procedure now for what we call simple m by n. I will call this as a composite switch, m by n composite switch, and we will try to find out how you will estimate the blocking probability for this thing. So far the number of calls are going to be less than n which are passing through this switch. This will remain in non-blocking state. The moment you get a call which is going to be number of calls will become equal to n. After that, any call comes in cannot be made through, it is then going to be in blocking state. We need to estimate that blocking probability, and for that we need to understand the queuing theory, basic fundamentals of that. So, in this case it is very simple the way we actually model it. Let me go to a simple queue and then I will come. So, what happens, queue is always represented in this fashion. So, there can be tasks which can come into the queue and they can be served. So, what we do is how the task will be arriving randomly, actually there is no deterministic thing. How you can actually model this particular task arrival process. So, what we do is we assume it to be a Poisson distributed phenomena. So, what do we mean by Poisson? That if you take a time interval, so you are starting from say time 0 to capital time t. So, how many number of packets will be arriving in this time interval t? So, what is the probability that k packets will be arriving? So, packet arrival is an instantaneous process. In one single instant a packet comes. So, two packets can come very close to each other, but since it is a point process, two packets cannot come at the same instant, there will be infinitesimally small gap between them, and we define a parameter called lambda here, which is the arrival rate. So, this is average number of packets which are going to arrive per unit of time. So, that is I think something which can be done. So, in capital time t, on an average lambda t packet will be coming. Now, the probability that k packets will be there in time t. So, probability for this will be defined as lambda t raised to power k e raised to power minus lambda t divided by k factorial. This is a probability distribution, and of course, one can verify that if I do summation of this, if I actually do sum of this over k, I should actually end up in getting equal to 1, which of course is obvious, because e raised to power minus lambda t can be taken out, and this summation, as all of us do know, over k, this summation is nothing but e raised to power lambda t. So, e raised to power minus lambda t and lambda t will give you 1 always. So, this actually is a probability distribution, and we call it a Poisson statistics. And of course, we can look at the same particular distribution in another way, that what is the chance that a packet arrives and the next packet arrives, what is the distribution of inter-arrival time, the time gap between them. If I want to find out the distribution of this, what should be the distribution? This actually can be derived from here, we call it exponential time distribution, and the derivation is again very simple and elementary. What I can do is, I can now take, let a packet arrive. What I can find out, at least packet is not arriving in this time period, I can find out this probability. So, if I know at least one packet arrives, this is not, that packet does not arrive in time t, this is means that probability that arrival time is greater than or equal to whatever is the t prime which I am taking. So, remember this is a cumulative distribution function. Once I take derivative, I will get the PDF of this. Probability that arrival time is greater than this actually means that 1 minus probability at least one packet arrives in this time distribution, okay, or probability that no packet arrives in this particular time distribution. So, that probability I can get from that Poisson statistics. So, this will be 1 minus e raised to power minus the, so probability no packet arrives in time t prime, that is what it means, and this will be, I just use the Poisson statistics. So, lambda t prime will be 0, e raised to power minus lambda t prime divided by 0 factorial, it will be e raised to power minus lambda t prime. So, that is a probability, or alternatively we can say is that probability that inter-arrival time, in fact CDF is always defined that probability of x being less than x, that is what is CDF, and then we take the derivative. Here I have taken it on the higher side, that t is greater than t prime, I should actually take where t is less than t prime. So, this implies that at least one packet should arrive, probability that at least one packet should arrive, I should have derived it this way, at least one packet arrives in time t prime, which is nothing 1 minus no packet arrives. So, it will be this thing. So, this is what is consistent definition with the cumulative distribution function. So, this is what is the CDF, and once you take the derivative of the CDF, you will get the PDF. So, once you do that, take the derivative. So, PDF of t prime distribution will be e raised to power minus lambda t will remain as it is, minus lambda will come out on this side, this is minus So, this is what it will be. At t is equal to 0, this value will be lambda, and then it will fall down, and we call it as the exponential distribution function. So, that is the inter-arrival time which is going to be there between the two. So, coming back to this q, so this arrival process is characterized by lambda. We also define an equivalent process which is for departure, which is technically nothing but again, if there are always packets, number of packets which will be departing, if packets are continuously there in the queue, that will also follow a Poisson statistical process, but we cannot do it because if there is no packet in the queue, that time the packets cannot go out. So, the outgoing process cannot be represented by Poisson statistics because that is dependent on the arrival process. So, what we do is we define a complete packet processing time. So, if a packet is there in the queue, so packet, the moment you start serving it, how much time does it take to serve the one full packet or for its transmission. So, that is essentially now we assume it to be exponentially distributed, and we define this distribution as this. Okay. So, average value of the distribution time or the time, average time which a packet takes for moving out is 1 over mu actually in this case. Okay. And usually what will happen is, if the packet, the process, if this queue is going to be empty for at least some fraction of time, if you observe for a longer duration, then the queue is stable. So, only when suddenly large packets will come, the queue will fill up, but if all the time packets are coming and you are not serving at faster rate, it means that mu is going to be smaller than lambda, then there is a problem actually. If mu is smaller than lambda, then q will keep on building to infinity, it will be unstable thing. We will actually prove it that it is what happens. So, this is also technically is a Poisson process, but only if the packets are continuously available, because packets will not be there some once in a while. We cannot use this kind of thing that number of packets going out is equal to this. This is only going to be true if packets are available all the time. So, technically it is also being derived from Poisson statistics. So, what you do is now we have to now build up what we call Markov chain for this, and we are going to assume a steady state condition. So, we define the state of this queue as being defined by number of packets which are there in the queue. So, the first state will be the state 0 when there is no packet. So, if I take a very small time, so now the time of observation is extremely important. If you are in state, if I am actually having a time interval delta t, and I will actually make this delta t goes to arbitrarily 0 value, but ultimately this will cancel out in the balance equations. So, the probability that a packet will arrive is defined by delta t by n factorial, and if delta t limit going to 0, then of course for value of 1, for n is equal to 1, the probability will be lambda into delta t. For higher order, higher probabilities, this value will, because now this argument will become 0 actually, so this will be 1, and for higher values the probabilities will become extremely small, it will become lambda into delta t square by 2 factorial and so on. So, these values can be neglected, they are very small, so I need not consider them. So, at any point of time when delta t is infinitesimally small, only one packet can arrive, and if that happens, I will be coming to state 1. So, you will never be going from 0 to 2, that is not possible in this case. So, similarly, a packet goes out, that probability will be mu into delta t, and you will come back to state 0. So, this happens at any point of time when you are observing. So, similarly, from 1 to 2, you will get lambda into delta t, that will be the probability, and this probability will be mu into delta t, and so on. Since I am actually taking infinite size q, so this can keep on happening. We in fact call it a Markovian arrival, Markovian departure, single server, there is only one server, and infinite buffer size, mm1 infinity q we call it. Now, under a steady state condition, the probability that you will be in certain state will be constant, which actually means if probability that I will find this system in this state 1 or state 2 are going to be constant. So, the probability, if I make any closed surface, the chances that you will exit out of this surface and you will enter into the surface has to be exactly same. That is a balance condition. Okay. So, this balance condition, if it is satisfied, will give me the steady state of, I can actually now use this particular thing to identify the state probabilities. I will exactly use the same thing later on to make an estimate for my m by n composite switch. So, in this case, if the P0 is the probability, steady state probability of being in state 0, and I make a surface something like this, which actually means lambda into delta t, this is a transition probability, then I am going out of this surface, this particular surface. And what is the probability of coming into the surface? That I am in probability of being in state 1 into mu into delta t, and I can see actually sorry, I have, so this delta t cancels out. So, delta t is actually immaterial. So, P0 and P1 they are related by ratios of lambda and mu, that is what is more important. Similarly, if I actually look at this particular thing, I can then same thing I can do it, P1 into lambda delta t is equal to P2 into mu delta t. You can do whatever surface you will be able to make, if they are say k states, possible states, you will be able to build up k minus 1 equations, and for k state probabilities you want to estimate, you require k equations. The last equation will be the first axiom of probability, that sum of all mutually exclusive events, the probability of those has to be equal to 1. Okay. So, we will use that axiom as the last equation, and then we will to get all state probabilities for a steady state system. So, again delta t goes out, same condition holds true. So, I can keep on extending this. So, which actually means I can write P1 as lambda by mu P0, P2 I can write as lambda by mu P1, which is lambda by mu square P0, n turn P raised power n will be lambda by mu raised power n P0, and n will go till infinity actually. So, now almost all equations I have, all probabilities I have now being represented in terms of P0, but what is P0? So, if I do P of I, summation over all possible i's, this should be equal to 1, which implies that P0 plus P1 plus P2 plus P3 and so on till infinity, this should be equal to 1, and I can write this as P0 plus lambda by mu P0 plus lambda by mu square P0 and so on lambda by mu raised power n Pn and so on. So, this should be also equal to 1. So, this is nothing but I got a series, and this is a geometric progression, and I can very well actually solve it. I can call lambda by mu as rho, and this value will be using a series thing. So, series says that so once I want to solve this particular sum, so series will be nothing but a b raised power total number of terms. So, that what should be the sum. So, I am just going to use that same formula, and I will end up in getting as, because a in this case is 1, rho raised power infinity minus 1 rho minus 1, and interestingly what I will find out, rho raised power infinity can be 0 only if rho is less than 1. So, P0 will be rho minus 1 divided by rho raised power infinity minus 1, and if rho is less than 1, then only I will get a solution which will be 1 minus rho, some positive value, and a probability of course has to be always less than 1, which will always be guaranteed if rho is going to be less than 1. If rho is 1, P0 will be 0, and of course rho is 1, P0 is 0, but 1 raised power infinity is also going to be undefined in that case. So, this becomes undefined. So, rho has to be less than equal to 1 for a stable situation. So, once I know P0, I can now actually find out all state probabilities with that. So, I have now got my P0, which is 1 minus rho, P1 which is rho into 1 minus rho, P2 rho square 1 minus rho, and so on. And henceforth I can find out what is the average Q length of this packet. So, average Q length, of course, I need only the state probability thing, because I will be using similar expression, similar procedure actually now to for m by n composite switch. So, average Q length in this case, because this will be required, so I call it L bar. This will be nothing but summation of that number of packets which were there in the queue I and what is your probability of being in state I. So, this is for all i's and this will be your L bar. So, this can be estimated again as I rho raised power I 1 minus rho, and I goes from 0 to infinity. And of course, you can solve this and you should get a value of rho 1 minus rho. I am not solving it, I am just writing down the result directly. The easier way to solve it, actually take the derivative, take 1 minus rho out, take the derivative, and then of course replace. That is the best way of doing it. So, I can try doing that, actually it is not. So, okay. So, let me do it in a slightly. So, 1 minus rho comes out straight, I is equal to 1 to infinity. For I is equal to 0, this does not make sense. I will have rho I 1 minus rho. I can take also a rho out, and of course, now this thing can be always written as and summation and derivation both are linear operators. So, I can always exchange them. So, I will end up in getting d over d rho summation of rho raised power I is equal to 1 to infinity. Now, this summation is again nothing but a geometric progression, with the first value is going to be rho in this case. So, it will be rho raised power infinity minus 1, rho minus 1, so rho raised power infinity minus 1, this thing actually will turn out to nothing but derivative of rho 1 minus rho that is what you will get. Remember, whenever you are taking 1 over 1 minus rho derivative, it will be minus 1 over 1 minus rho square and minus rho again. So, it will become positive actually. Yeah, that is how it will be, and I can solve it. One minus rho plus rho, this cancels with this, I will end up in rho over 1 minus rho. So, that is what was the result which I wrote here. So, this gives you the average Q length, and you can actually now plot rho into 1 minus rho is equal to L bar, and that is when rho is equal to 1 and rho is equal to 0. This goes from 0 and then this explodes and goes to infinity. So, Q becomes unbounded, it will not be bounded in length, and it will be unstable at rho is equal to 1. So, we will use the same now technique. Essentially these are basics of, I think everybody in queuing theory does this thing first. Now, we need to do it for m by n composite switch. Now, here what is happening is a call actually arrives. So, call request arrives and those arrival will happen. Now, you have to understand, if whatever has a free ports, only call can arrive on those. Once a call arrives, that line is now busy. So, if you look at a telephone line, if a call arrives, call will now remain hold and line is now occupied till the call is over. The person is now talking for this period, and when call is over, again line is free, then only the new call can arrive. So, in this period no arrival is possible in the line actually. So, arrival is only possible for the free lines. So, but for a free line, when a line is free, what is the arrival rate? So, I can take some lambda. So, if there are n free lines, my arrival rate will be n into lambda. So, lambda is the arrival rate on single thing. Now, once somebody is talking, usually what I am assuming is the person, when he talks, the duration of his talk is now exponentially distributed, which actually means this call completion takes on an average 1 over mu time. So, what I will call is a call departure rate is mu, okay, for every line. So, if there are k lines which are occupied, which are busy, which are being talking, so k here also going to be occupied, connected to these. So, k into mu times will be the departure rate in this case. So, k into mu into delta t is the probability of coming from state k to k minus 1. Once you go to k minus 1, it is k minus 1 into mu into delta t, and similarly arrival rate is going to be whatever is the number of free lines. So, if number of free lines is L, so it will be L into lambda into delta t. Now, that will be variation here, and the state of this m by n composite switch, it is m by n cross bar technically, and only n connections can be put on the outgoing ports. So, the state of this particular switch is being governed by number of lines which are occupied here at the outgoing port. You cannot have more than n lines, that is not possible. M, because m has been taken as larger than n. So, it is not possible to have more than n line getting occupied, and after that even if a call arrives, it has to be dropped, it cannot be taken up. So, it is a blocking system, and you do not have the way we had in a queue. You could have infinite packet being queued up, here that is not possible. You can only have till n, and after that even if call comes, you cannot hold it, actually it is gone. So, you are in the blocking state. So, your queue will have only capacity of n here. So, that is how m by n composite switch can be modeled with this particular thing. So, let me now build up a Markov chain for this entity. So, your m by n composite switch is going to be, so there is no call there. So, the arrival which can happen will happen with the rate m lambda delta t. Remember, delta t again is going to cancel when I am going to have a balance equations to be built for steady state situations. Okay. So, I need not, I can actually remove delta t. In fact, earlier time the delta t cancels out from both sides, I need not keep it. So, in fact, when I have built the Markov chain, I could have removed this delta t without any problem, kept. Now, that is what actually is being shown in most of the places. So, I need not keep, I just keep the rates here. So, it is proportional to rates and so on. And of course, if one call arrives, you will be in state 1, and then how you will come back to 0? Delta t. So, I am now going to remove delta t because of the reasons which I have mentioned, I need not keep it. Then if you are in state 1, so one call is coming in, one call is through, so the only now m minus 1 lines are available on which the call can come, and here n minus 1 lines are available. So, if the next call comes, this will come with a rate m minus 1 into lambda, that will be arrival rate, and from state 2 you can transit back to state 1 with 2 mu now. So, remember this instantaneous probabilities are fixed, and only one call can be completed at any point of time. So, if 2 to 0 will always happen from 2 to 1 and 1 to 0, that is the way it is always going to happen, because the delta t is in limit is going to 0. So, from 2 I can come to now 3, and this will be m minus 2 into lambda 3 mu. Perfect, I can keep on doing it, but for how long? Ultimately, remember, I have the maximum size, n minus 1 calls can be set up. And when the nth call is set up, you have had only one line free, so it has to be lambda, and you can go to with n mu, and after this, even if arrival happens, you will come back to the same state, does not matter after this. So, with this transition probability, this actually loop backs m minus n lambda arrival, you come back to the same thing, you do not change the state. Okay. So, this here actually now, this should not be lambda, but this should be m minus n minus 1 lambda actually. Sorry, I need to correct this. And you can actually now note that the sum of these two, if you make m minus 3, forget lambda and mu in this case, m minus 3 plus 4, this will be m plus 1, m minus 2 plus 3, m plus 1, m minus n, I think it should be n plus 1, yeah, m minus n plus 1 plus n, m plus 1. So, that is how you can verify. This will be the Markov chain for a composite switch. And of course, now I can write down the balance equations and then solve them and then get the probabilities. So, let me do that. So, I am going to build up first of all this surface P0 into m of lambda should be equal to P of 1 into mu. So, which implies P of 1 is m lambda by mu P0, that is what you will get. If I make the second surface like this, or you can make a surface like this also, does not matter. Ultimately, you will be actually now cancelling all the terms and trying to get all state probabilities in terms of P0, and sum of all probabilities will be always equal to 1. That is the way it is going to evolve. So, P of 2 now in terms of P1 I can write m minus 1 lambda, sorry, it has to be P1, P2 into 2 mu. So, that is a transition rate at this surface, which will give me P2 is equal to m minus 1 lambda divided by 2 mu into P1 m into m minus 1 2 into 1 lambda by mu square P0. Keep on doing it. So, P3 similarly will be m into m minus 1 into m minus 2 3 into 2 into 1 lambda by mu cube P0, and of course, you can clearly observe what is this is combinatorial MC 3 lambda by mu 3 P0, and in general I will have Pn is equal to MC small n, n has to be actually smaller than n, lambda by mu raised power n P0. So, now at this point actually let me stop, and we will now take up this thing further and try to understand how to compute call congestion probability and time congestion. I will also define those two terms in the next lecture.